you should have a larger circle that goes through two sides that do not include the other sides in the circle. I mean, that is mentioned.
It's not necessary
here.
to do arrow.
But what I want to tell you is that because we move this one very, very small, so small that the center is almost still at Q. We want to see if there's a possibility for any edge that come out of Q. So when you move like that circle should, how should I say, still move very slowly, right? So it should still almost, I probably shouldn't draw this one like tangent to L. I should say it's close, it's almost touching this thing.
You can draw a circle passing through PI and PK.
PI and PK.
And the PK will be outside this circle, and the circle will intersect with arrow twice. And that's what the inductive edge is.
PI and PK. The PI, PJ, and PK, they have left-right relation. Okay, the most left one, the leftist one is a PI, right? The rightmost one is a PK, right? The center one is PJ, right? So when you talk about remember I talked about like the relation between the parabola. Parabola has like the order, I mean the left, right, order. So what I mean is like when you consider the edge, okay, you consider the consecutive parabola. Okay, you don't consider like okay, the parabola, and separate.
That's the new parabola appears, right?
I mean, what we want to show you is that okay. What you want to draw is something like here. But what I want to tell you is that, okay, you should consider these two first, and then these two. Okay? You don't directly consider, what should I say? What you are considering is actually like this one and this one. If you directly consider these two, what happens is that, okay, there shouldn't be any parabola in between. Okay. When you consider the edge induced by vertex, you consider the consecutive parabolas. Okay? So you consider this part, this pair, and this pair. Okay? Not this one. I mean, if you consider this one, then it's kind of like you omit this one. When you omit this one, of course, it's okay. Why? Because, well, you don't have this parabola breaking this.
The parabola breaking the original parabola will induce the edge.
Yeah, exactly. It will induce. Original is break here. It will induce edge here. It will induce edge here.
Not like that. It will.
No. It doesn't. Okay. The induction is like this. So the induced edge. Maybe I use the other So this is like the induced line are these straight lines, not a parabola. Okay, don't be fooled by a parabola, because eventually the lines that you induce for the Borel diagram, they are all straight lines, at least for those point sides. The induced lines are all straight lines. Okay, so look at look at here. Every lines are straight lines, right? You don't have the parabola. I mean, the parabola, the pitch lines are there, okay? I mean, during the induction, yes, but how should I say, like the intersection of consecutive parabolas will actually draw a straight line. Okay, even though those parabolas, the shape will change, but eventually they will induce a straight line. The consecutive parabola will induce straight lines. So this is a little bit, you need to be very careful. When you talk about the induced line or parabola, these are two different things. Yeah. So I mean, remember, like because we use the straight line. So with the straight line that gets induced, that we consider here, are induced by the consecutive parabola. I mean, when I say consecutive parabola, I mean like in between left and right relation. So that is why I emphasize, okay. I emphasize that here, the PI is leftmost, PJ is middle, PK is rightmost. So if you will induce certain lines out of this Q, you should consider PI, PJ, and PJ, PK. Okay? If it's something like you have original, you have this. Okay. Before it breaks, this two before it breaks, try not to look at this. Before it breaks, you should have a straight line that gets induced by these two parabola. Okay? That's exactly what you are talking about. Because before this parabola break out, okay, you should have these two parabolas are neighboring to each other, right? That's PI, that's PK, right? That's exactly what you are considering here. So they will induce a straight line, yes. But when this one breaks out, it will induce two lines. This one by PI, PJ, this one by PJ, PK. Supposedly. But I'm trying to use this one to tell you, okay, a very, near point here, it's impossible to appear. The very near point here, it's impossible either. So you just have no way to induce like these two edges. But if that's no way to induce edges, how can this point be the vertex?
Why do edges are like that? Even like this.
No. Let's now look at this one. Before this one breaks in, okay, you only have two parabola. How can you have two parabola to come up with two edges? The join of two parabola can only have one line. Right? Can you draw two parabola that create two lines for me? Because that's what happens. Okay, those parabola, okay, when they have a joint, that means, okay, let's now look at this one. Okay, when these two parabola meet here, what does that mean? The distance to this one and distance to this one are the same. Right? That's exactly what we have for the first property, right? Okay. Then put it this way, okay? You try to remember, try to understand this first. You have to understand this. But you don't apply this, I mean, in understanding, then it doesn't make sense. It doesn't make any good. Okay? Because you have to apply this, as I said. Okay? I mean, if you have, two parabolas, okay, in the joint will, so it's going to be something like this. Okay, from here, when you keep going down, you will form one line for these two parabola, for these two consecutive neighboring parabola. Okay. You have trouble understanding this, right? Because you think these two should lead to more than one line. Then I will ask you, draw one example for me. Okay? The easiest way to respond to your question is, you try to, because sometimes you cannot, you don't understand, but you should try to draw this geometry yourself. And then you should later become clear to you why this is the case. Okay? So, yeah. I'm sorry, it's 11 already. Let's take Terry's break. When we come back, we'll continue the discussion. Okay? Sorry.
这个空间，是这个推这个，这个推这个，然后塞进去，然后所以这两个推起来，会让这个东西会让这个小一等变成小一等于方方变成双键。就因为只有因为这只有两个方方，小一等，那小一等于的方方都会倒出来，这边有小一方方，所以就可以写双键。这个，所以小一点的方法就变成双键头前，然后变成双键，那就有两个双键。那你打吗？我他们挂了，我就觉得都挂了，挂了。这一半那个没有，变成下午这个代表可以用也。可以就会死。
Okay. So we talked about the side event already, right? There's another event that we need to discuss, which is exactly the opposite of what we just mentioned that was impossible. Okay. When will arc disappear? The second type of event, we call that circle event. That is, okay, you can see, okay, when we go down, this straight line go down, you can see some arcs may become smaller and smaller eventually. Again, let's assume like these three consecutive arcs, their sides are Pi, Pj, and Pk. And when the side, when this L straight line goes down, okay. I mean, here we assume that this arc will become smaller and smaller, and eventually it will vanish. It will vanish and make the Pi and Pk neighboring to each other. Okay. So right before or right at a time when this middle arc disappeared, it is exactly what happened. Okay. Pi, Pj, and Pk will be on the same circle. Okay, will be on the same circle. So it's going to be something exactly like this. Okay, but when this line goes down, it's not like we will trace the edge here. It's actually just like what you said earlier. It will trace only one line, which will come out from Pi and Pk. So that's this. Okay, so this is possible when the L goes down. But the previous case, you want to trace two edges, one for Pi, Pj, the other one for Pj, Pk, is not possible. Okay, so hopefully, if you understand this, it will also help you to understand why this case is not possible. Okay, so remember, in straight line algorithm, okay, even though I say this is the variant of the straight line algorithm, but we still have events to take care, right? I mean, we still have the events to take care. So we have two events, okay, and this event is obviously, I mean, it's okay. So we will actually have, remember, like I told you, in straight line algorithm, there are two things that we take care of. The first one is event, which governs how the straight line goes down, right? The second one is the data structure that we maintain. I mean, either the left-right relation or something like that. So in this case, it's a relation, it's a neighboring relation, the left-right relation of the parabolas, which, or you can call that the status of the pitch line. Okay, and for the event, okay, we have, as I said, we have two events. One is side event. The other one is this circle event. So this circle, the side event can be easily had. Basically, each side had one side event, obviously, right? Okay, so we know that when the sides, those side locations are even, and obviously we will deal with that according to their y coordinate value, right? But how about this circle event? The circle event actually will be created. They will be created like on the fly. How do I mean? I mean like for every 3 consecutive arcs, we will compute where this circle event is going to happen. Because we have 3 points, right? We have 3 points when we have the three sides for the consecutive arcs, then we know exactly when this circle event will occur. Basically, it's like it's the joint location and the distance, like this much, okay, which is the R below the joint location or the center of this circle. R below the center of the circle. So this is where the circle event is going to occur. For every three consecutive arcs, you try to insert this thing into the event queue, okay, into the event queue. Of course, some of those may not happen. Why do I say that? Okay, it's because, okay, for example, let's say we have 4 arcs. Then you will create, for example, like you'll try to find one circle event location for these 3 sides, right? For these 3 sides, and another one for these 3 sides, right? Because they are, every 3 of them are consecutive, right? But only one of them may really occur, because when it goes down, okay, when it goes down, maybe this one will vanish. Maybe this one will vanish. When this one vanish, it becomes like right? It becomes this one has vanished, gradually disappeared. And well, in that case, is this side event? Is this circle event that occurs here, right? But when this occurs, obviously, the circle event for these 3 parabolas, well, shouldn't be considered anymore, right? Because well, one of them is gone, right? One of the circle that contribute to this is gone. Okay, so what happens is like yeah, we insert every 3 consecutive the side circle event for every 3 consecutive parabola into the event queue, and we keep track. If those parabola that contributing to this event are still active. If they are still active, we consider it. But if, for example, after this one is gone, okay, when the circle event of these 3 happens, say it's here, at this point, yeah, I mean, it occurred. It tells you, oh, we have a circle event here. So when you get this event point out of the event queue, but you will find that one of them, okay, one of the arc is no longer active, right? So you don't deal with it. You just skip it. Okay? Be very careful here, okay? So basically just these 2 different events, okay? So the L, by the way, I forgot to mention one thing, okay? We also have this, okay? So the number of arcs, okay? This one, the fact that number of arcs, I mean, in the parabola will be limited by 2n minus 1. Okay, why? Because, okay, an arc can at most break, let me show you this one. Okay, when you have a side event, this side event may break this arc into two pieces, right? That's like the only possibility that this a new arc occurs, right? Right? So think about this. You have only n sides, right? You have only n sides. So say each side when it is created, it will break the previous and this one arc into two pieces. Okay, including the original one it has. So it's going to be how many? Okay, so when it breaks the previous side into two, okay, so it has at most 2n, right? Okay, but you need to, you know, for the last side event occur, there's no way for that last arc to be broken by another side event because that's the last one, right? Okay, so every previous arc could be broken into two. That in the worst case, right? So it's going to be, you know, 2 times n minus 1 plus the last one. So it's going to be 2n minus 1. Okay? I forgot to mention about this because obviously we spend too much time discussion on if that discussion help you understand better, it's good. It's all good. Okay. So back to the discussion. Okay. So now let's talk about this algorithm. But I think I mean the algorithm basically is very similar to any plane algorithm that we have talked about. So that it's you can see we have 2 data structures. One is like standard structure T. That standard structure keep track of the active parabolas for each mount. Okay, and the other one is there's a Q, event Q. Okay, that control the event according to the y coordinate of every event point. Okay, and at the beginning, of course, we insert all the site location into the event Q. Okay, and then every time we encounter a site, we have we need to deal with handle site event, and every time we create a site event, we need to insert event. We need to see we need to insert like additional circle event point into the event queue. Okay, because once we have a new site, new arc, I mean we may have we may need to consider like 3 consecutive arcs, the new 3 consecutive arcs, and we need to insert those into the event queue. Okay, and for every circle event, we deal with the removal of an arc from the tree, from T. Okay, and of course after that we also need to mark like certain arcs are no longer active, so that like later on when those circle event appear, okay, we need to know when to some of them have to be skipped. Okay, so that's pretty much about it. So these are so this is like how we handle the side event. As I said, like I think we have like most of them. But one thing that here we actually describe it in much more detail because we actually try to maintain a doubly connected edge list. So when we create a side event, actually we will try to draw the half edge, the 2 half edge out of that point, because we are when we have a side event normally it means like yeah, because it means there's a new arc, right? When there's a new arc, what is that? What does that mean? Because consecutive arc will induce two straight lines, right? So we need to, when we have a side effect, because of that new arc introduced, like we have to, get ready to create two additional half edge in the doubly connected entities. So those details are also described in the algorithm, which actually I didn't really spend much time talking about that because really those are details. I mean, if you want to know more detail, you are welcome to check out the algorithm yourself. But I think conceptually, those are just like some bookkeeping work, okay, which shouldn't be too difficult to understand. And we also assume, okay, there's a bounding box, okay, for all the sides. So we assume like originally we already start from the bounding box, the doubly connected entities. Okay. The other parts I think that we already explained. And this is a handle circle event. So yeah, we will store the Roland diagram, okay, in subdivision with a large bounding box. To be exact, we will use doubly connected edge-list data structure to store it. And each line, is stored in a tree which can be easily searched for the left-right relation. For example, for a given parabola, it takes log n amount of time to search for the neighboring parabola. Okay, and also like we have an event queue, okay, which store the the events and will deal with the events according to its y coordinate from largest to lowest. Okay, and there are two types of event: side event, circle event. Okay, so we have only a little bit more than 5 minutes. Okay, so so far, okay, we talk about all the regular cases. There are two degenerate cases that we could consider here. Okay, if we have more than 3 points on the same circle, okay, it is possible, right? It is possible. But what happens? In fact, the algorithm doesn't need to change anything. Okay, because say we have 4 points on the same circle. Okay, like this. Say with these four arcs, their sides happen to be on the same circle. So what happens is that we are going to deal with, say this is the side of the torso. So we are going to deal with these 3 first, right? And because it's a circle event, so well, the middle one is gone. The middle one is gone. So eventually it's going to be this one. So this middle one is gone. You would have think like this. You would have think like this. But in fact, what happens is that not only this one is gone, but also this one is gone too. Okay, but that's fine. When you consider the doubly connected edge-list, it's going to be something like this. Okay, it's going to be okay. We have 2 points that happen to be on the same place, and then we have half edge that has 0 length. Okay, so but it does not affect the correctness of the algorithm. Okay. Of course, this type of 0 length half edge is bothering us, right? So if you do not like it, you can, after you create this thing, okay, you can you can go through the whole doubly connected edge list data structure to remove this zero length half edge. You know, you just do an additional process to get rid of that. But the algorithm itself doesn't need to do any change. Doesn't need to require any change. The algorithm. Okay, so that's fine. Okay, that's for the the first case with more than 3 arcs, 3 points are on the same circle. Okay, the second one is that we talk about like the side event occurs which breaks the arc into 2 pieces, right? But how about if a side happens to be located exactly below the breakpoint between 2 arcs? Forget, okay. At this moment, say this is the 2 arcs, and the joint is here, but this joint happened below this joint happened there's a side. Okay, occur exactly like this. Well, so what happens is that, because you are considering what happens is like this. You are considering this point side event to break this arc. This arc. So what happens is that, this is the case. But this L moves down. You just consider this arc. It's like broken into 2 pieces. Of course, you will find that this arc, eventually will be something like this. This is new one. This is new one. This is contributing from that new side. This is contributing from that new side. Well, actually, this should be much. And this. But you may think, but when I say this side event, it breaks this arc into two pieces. Well, we only see the left piece, right? How about the right piece? The right piece is actually length 0. Length 0. But again, it's fine. I mean, we just consider that arc is 0 length. But that 0 length, what happened is that, because it's 0 length, then remember every side event or circle event, we will always reconsider the 3 consecutive arcs to decide, there's an additional the circle event, right? So right after the insertion of this, as I said, you are going to have a 0 length of the arc here. So that 0 length of arc, along with this new arc and the new arc, the 0 length of arc, and this left arc, it will create a circle event. I'm sorry. Sorry. It's this one and this 0 length and this right arc. It's going to create a circle event, which happens to remove this 0 length arc. So the whole thing will be correct. Okay? Yes. Sorry. What's your question? Oh, okay. So basically, So I just want to point out to you the algorithm here. We do the handle side event first, right? And then we do the handle circle event. If you ask me, can we change the concept, this order? Guess if you can do that or not. Anybody? No. Exactly, because of the reason I was talking about. I mean, when you have a side effect, you may create a zero-length arc, which will immediately create a circle event that get rid of that have zero-length arc. Okay? So this order is not arbitrary. This order is not arbitrary. You have to deal with side event first and then circle event. Because there are certain things that this order may affect the result. For example, like the second degenerate case. Okay, the second degenerate case. So a question like this, if I ask you in midterm, can you answer? I'm not asking you to memorize stuff, but if you understand the algorithm, I mean, you should be able to tell me. I mean, can I change the order of this? Because these all the events are handled based on the y volume. But if you understand the whole algorithm well enough, you should tell me. You cannot change the order because of what? Because of the second degenerate case, which gets handled correctly only under this order. Okay? Well, I mean, so Fortune's algorithm, okay, the Voronov diagram of set of endpoint sites in a plane, okay, can be computed with a 3-line algorithm. Okay, it takes big O n log n time using big O n linear storage. It is linear storage because why? Because the fish line, as I said, the most number of fish line is linear, right? 2n minus 1, right? And we have a linear number of vertices, linear number of half edges. I mean, edges or half edge, whatever you call it. I mean, and the size as well. That's even, right? So the storage is linear, obviously, but for the 3-line algorithm, because I mean, we have for 3 consecutive points. I mean, we consider their circle events, right? So circle events and the side events plus the side events, the total number of events should be bounded by linear as well, right? Okay, bounded by linear as well. And then, okay, each event takes log n amount of time to take it to handle it. So the total is n log n. Because you are talking about the priority queue, right? Priority queue, each operation takes log n amount of time. Okay, so basically it's n log n. So this is actually a very good algorithm. So unfortunately, I don't have time to talk about. I will cover this in the next week's lecture. Okay, we can actually deal with we use a Voronov diagram concept on like not only the point size but also the line segments. Okay, so we are going to talk about this, and also we can also consider this is the nearest point Voronov diagram. We can also consider furthest point Voronov diagram. So there are two variations of this this thing. Okay, and each of them has like its unique applications. So because of time constraints, as I said, like this chapter it will just take a lot of time. Maybe it will take the whole chapter, whole lecture next week to finish it. Anyway, okay, I will give you the second, the third homework. Okay, on the E class. So let me repeat. Okay, don't look at the end of the slides homework. Okay, the first homework is like that, But other than the first homework, never look at the end of slides for homework. For example, I mean, at the end of the slides, I have the homework here too. But don't look at this. I will give you the homework on the E class. Okay? Okay, so disregard this, please. Okay? So, any question?